Welcome to information theory. To understand entropy, we must first answer a fundamental question. How do we measure information? Intuitively, you might think of information in terms of file sizes, bytes on a hard drive. But in communication theory, information is actually a measure of surprise. Let's look at 3 messages. First, imagine receiving a text that says, "The sun will rise tomorrow." How much information did you actually gain? Almost none. You already knew this would happen with near absolute certainty. It's predictable and therefore uninformative. Now, compare that to a message saying, "It will rain today." This carries more weight. There was uncertainty. It might have been sunny, it might have rained. This message resolves that uncertainty, so it contains more information. Finally, imagine you get this message. You won the lottery. This is a shock. It describes an incredibly rare event. Because the probability of this happening is so low, the amount of information, the surprise factor, is massive. This is the core intuition of entropy. Information is not about the length of the message, but about how much uncertainty it removes. To quantify entropy, we first need to talk about the concept of surprise, or information content. Intuitively, there is a fundamental trade-off at play here. Imagine a balanced scale. On one side, we have probability, p, and on the other, we have the information or surprise, I, that we gain from an event. Consider an event with high probability, like the sun rises tomorrow. Because we expect it to happen, the probability is heavy. But notice the other side. The actual information we gain from observing it is light. It's not surprising, it tells us very little we didn't already know. Now, let's flip the script. What if we observe a low probability event, say a solar eclipse appearing out of nowhere? The probability is tiny, a mere feather on the scale, but the surprise, it is massive. The rarer the event, the heavier the information payload. In information theory, seeing something unlikely provides significantly more data than seeing something predictable. This brings us to our core definition. Information is inversely proportional to probability. If p is high, information is low. If p is low, information is high. We will use this relationship to build the equation for entropy. Building on that feeling of surprise, let's formalize it. We know that information or surprisal is inversely proportional to the probability of the event. If an event is certain, p is 1 and there is no surprise. If p is tiny, the inverse is huge, and the surprise is massive. But we need more than just a proportionality. We need a precise measure that makes sense for communication. Specifically, if we see 2 independent events, the total information should be the sum of their individual surprises. Since probabilities multiply for independent events, but we want information to add, the mathematician's tool of choice is the logarithm. We define the self-information as the log of that inverse probability. Now, using the rules of high school algebra, we can pull that fraction apart. The log of 1 over p is simply negative log of p. This is the fundamental equation for self-information. When we use a logarithm with base 2, the resulting units are bits. This formula tells us exactly how many bits of information a single event gives us. To quantify uncertainty, we have to bridge the world of probability with the world of information. Consider 2 independent events, A and B. In probability theory, the probability of both happening is the product of their individual probabilities. But intuitively, information behaves differently. If you learn 2 independent facts, the total information gained should be the sum of the information in each fact. So we have a structural mismatch. Probability multiplies, but we need information to add. This is exactly why we use logarithms. The logarithm is the mathematical translator that turns multiplication into addition. If we define information as the logarithm of the probability, the log of a product expands perfectly into the sum of the logs. This ensures that when probabilities multiply, the information content simply adds up, satisfying our intuitive requirements for measuring uncertainty. To quantify uncertainty, we need a fundamental unit of measure. Let's start with the simplest possible random event, a fair coin flip. Here, the probability of getting heads is exactly 0, 5 or 50%. Now, how do we measure the information contained in this outcome? We use Shannon's formula. Information, I, is defined as the negative logarithm, base 2 of the probability p. Let's calculate it for our coin. We substitute 0, 5 into the equation. To solve this logarithm without a calculator, it helps to rewrite the probability. Recall that 0, 5 is the same as 1/2, which is 2 raised to the power of -1. Logarithm rules allow us to pull that exponent out to the front. The negative signs cancel each other out, leaving us with a value of exactly 1. This result gives us our fundamental definition. An event with a 50-50 probability yields exactly 1 bit of information. This is the atom of information theory, the resolution of a single binary choice. Moving from single events to the bigger picture, let's consider where this data comes from. We call this an information source. Unlike a single coin flip, a source generates a continuous stream of symbols over time. Notice the pattern here. The symbol A appears frequently, while C is quite rare. From our previous definition, we know that each of these symbols carries a specific amount of surprise or information. The rare C hits us with high information, while the predictable A's contribute very little. But here is the challenge. How do we characterize the information capacity of the source itself, not just the specific message it just sent? We need to find the average amount of information we expect to get from every new symbol this source produces. In information theory, this average is called entropy, denoted by H. Ideally, it represents the expected value of the self-information. To calculate this, we sum the information value of each possible symbol, weighted by the probability of that symbol occurring. And since we know information is the negative log of probability, we arrive at Shannon's famous equation for entropy. This formula tells us the fundamental limit of data compression for this source, a concept we will explore next. Building on our understanding of bits and uncertainty, we can now formalize the heart of information theory. This is Claude Shannon's formula for entropy, denoted by H of x. It may look intimidating, but it is built from the very pieces we've just explored. First, look at this log term. As we saw earlier, the log base 2 of probability measures the surprise or the number of bits required to encode a specific outcome. But we are not just dealing with a single outcome, we have a whole set of possibilities. So we multiply the bit length of each outcome by its probability, how likely it is to occur. Finally, the summation symbol tells us to add all these weighted values together. Mathematically, this is an expected value. In plain English, entropy is simply the weighted average amount of information produced by a source. It tells us the average number of bits we need to convey a message from this source, setting the absolute limit for data compression. To really understand how entropy behaves, let's look at the simplest possible system, a binary choice, like a coin flip with probability p. Mathematically, the entropy H is defined by this summation. It looks complex, but let's visualize it to see what it's actually telling us. We'll plot this on a graph. The horizontal axis represents the probability p of getting heads, ranging from 0 to 1. The vertical axis represents the resulting entropy, or our level of surprise. Now, let's trace the entropy value as the probability changes. Notice the shape. It rises steeply, curves at the top, and falls back down symmetrically. Let's pause right at the top. This peak occurs exactly when p is 0, 5. This represents a perfectly fair coin. Because the outcome is most unpredictable here, the entropy is at its maximum, exactly 1 bit. But what happens if the coin is rigged? As we move towards the edges, the probability approaches 0 or 1. If p is 1, we know for certain it will be heads. There is no surprise, and therefore, the entropy drops to 0. This graph encapsulates the core of information theory. Entropy measures uncertainty, peaking when we know the least, and vanishing when we know the most. Building on the fair coin example, let's see what happens to entropy when we remove some of the mystery. Consider a heavily biased coin. Here, the probability of heads is high, 0.9, leaving only a 10% chance for tails. Intuitively, you already know what's likely to happen. There is less uncertainty here than with a fair coin, but does the math reflect that? Let's bring back Shannon's entropy formula. We need to sum the weighted surprise for every possible outcome. We substitute our values. The blue term represents heads, 90% probability times the log of 90%. The red term is tails, 10% probability times the log of 10%. Now, look at the surprise values inside the brackets. The log of 0.9 is a tiny negative number. Since heads is expected, seeing it provides very little information, very little surprise. Conversely, the log of 0.1 is a much larger negative number. A tail is shocking, but it happens so rarely that it contributes very little to the overall average. When we sum these up, the total entropy is approximately 0.469 bits. Notice that this is significantly less than the 1 bit we got for the fair coin. This confirms our intuition. As a system becomes more predictable, its entropy, its average information content, decreases. We don't need a full bit to describe the outcome anymore because we can guess heads and be right most of the time. Let's deepen our intuition. If entropy is a measure of uncertainty, a natural question arises. What arrangement of probabilities gives us the maximum possible entropy? Consider a system with 4 possible outcomes. On the left, we have a uniform distribution. Here, every outcome is equally likely 25% each. It's like a fair, four-sided die. Because the probability is spread out perfectly evenly, we have no way to predict the outcome better than a random guess. If we plug these probabilities into our entropy formula, we get exactly 2 bits. This represents maximum unpredictability. Now, compare that to the distribution on the right. This is a skewed distribution. Here, the first outcome has a 50% probability, while the others are much smaller. The mass of the probability is concentrated. Because one outcome is dominant, we can make a better guess. We are less surprised on average. Consequently, the entropy drops. Here, it falls to roughly 1/75 bits. Visually, the flatter the distribution, the higher the entropy. The more spiked or concentrated it is, the lower the entropy. Therefore, for any given set of outcomes, entropy is always maximized when the distribution is perfectly uniform. Now, let's build an intuition for what entropy actually measures by playing a game of 20 questions. Imagine we have 4 possible outcomes, A, B, C, and D. In our first scenario, the universe is uniform. Each outcome has an equal probability of occurring, 1/4. To guess the outcome, we need a strategy. Since they are all equally likely, the most efficient approach is a balanced decision tree. We ask a question to split the group in half, and then another to find the specific item. Notice that no matter which item it is, A, B, C, or D, it always takes exactly 2 questions to find the answer. In this uniform case, the uncertainty is maximized, and the average number of questions needed is simply the logarithm of the number of outcomes, 2 bits. But what if the game is rigged? Let's change the probabilities. Now, outcome A happens 50% of the time, B is 25%, and C and D are rare. If we use the old balanced tree, we are wasting effort. We can design a smarter tree. Since it is so common, we should ask about it first. Is it A? If yes, we are done in just 1 question. This happens half the time, saving us a lot of work. If it's not A, we proceed to check for B. And only if it's neither do we spend 3 questions distinguishing between C and D. This is the essence of entropy. It's the weighted average of the questions needed. Half the time, we need 1 question. A quarter of the time, we need 2. And for the remaining rare events, we pay a cost of 3 questions. When we sum this up, the average drops to 1/75 questions. Because the distribution was skewed, the entropy is lower. We have less uncertainty, so we need fewer binary questions or bits to describe the outcome. We have explored how entropy quantifies the uncertainty of a single variable. But in the real world, we rarely deal with isolated data points. Data often comes in pairs or larger sets. This brings us to joint entropy, denoted as h of x, y. Mathematically, it looks very similar to our single variable definition. It is the expected value of the logarithmic probability, but now, we sum over every possible pair of outcomes, x and y. This equation gives us the average amount of information needed to specify both variables simultaneously. To visualize this, let's use an information diagram. Imagine this blue circle represents h of x, the uncertainty contained in variable x, and this red circle represents h of y, the uncertainty in variable y. Notice that we've drawn them overlapping, implying these variables might share some information. We will explore that overlap soon. For now, look at the entire shape formed by both circles. The joint entropy h of x, Y corresponds to this total union. It represents the total uncertainty of the system, the information required to describe the outcome of X and the outcome of Y together. Continuing from our look at joint entropy, let's refine our perspective. We have our two variables, X and Y. Now, suppose we receive a message or perform a measurement that tells us the exact value of X. X is now known. Because X is known, there is no longer any uncertainty in that circle. But notice what happened to the intersection. Since this shared information is part of X, knowing X means we automatically know this part of Y as well. That uncertainty has vanished. So what is left? What represents the uncertainty of Y, given that we already know X? It represents the information in Y that is completely independent of X. We call this the conditional entropy, written as h of Y given X. Mathematically, think of it as simple subtraction. We started with the total uncertainty of the system, the joint entropy, and we subtracted the uncertainty we resolved by learning X. This leaves us with the conditional entropy, the quantity of uncertainty remaining in Y after X is revealed. Building on our understanding of individual and conditional entropy, we arrive at the core measure of correlation, mutual information. This quantity, denoted as I of X and Y, represents the intersection of our two sets. It quantifies exactly how much information variable X tells us about variable Y. But how do we calculate this intersection using the tools we already have? Intuitively, it is a reduction in uncertainty. Imagine starting with all the information in X, represented by this entire blue circle. If we then subtract the uncertainty about X that remains after we know Y, the conditional entropy h of X given Y, what are we left with? We are left precisely with the overlap. This is the information shared between them. This relationship is beautifully symmetric. We could just as easily start with the entropy of Y, subtract the conditional entropy of Y given X, and arrive at the exact same result. High mutual information means knowing one variable resolves a lot of uncertainty about the other. If they are independent, this intersection vanishes entirely. To rigorous formalize this relationship, we use what is known as the chain rule for entropy. Mathematically, it states that the joint entropy of X and Y is equal to the entropy of X plus the conditional entropy of Y given X. But let's see what this actually looks like. Imagine this entire bar represents the total information contained in the pair XY, our joint entropy. This is the total uncertainty we want to resolve. First, we learn the value of X. This gives us h of X bits of information, covering this portion of the total uncertainty. Now, what is left? The remaining space corresponds exactly to the uncertainty of Y that still persists after we know X. This is the conditional entropy, h of Y given X. So, the chain rule is really just a statement of additivity. The total information is simply the sum of the information in X and the new information provided by Y. Moving from the abstract definition of uncertainty, let's look at a concrete application. Data compression. Suppose we have a raw data source generating a sequence of symbols, like this string of letters. To store or transmit this, we must pass it through an encoder and translate it into a stream of binary digits, zeros and ones. The simplest strategy is to assign a unique binary code to each symbol. For example, let's map the frequent letter A to a single bit, 0, but for other symbols, like B, we might need a longer code, say 1-0, to keep it distinct. As we encode the rest of the message, assigning codes to every letter, the binary stream grows. The fundamental challenge of information theory is simple. How do we choose these codes to make this final stream as short as possible? Entropy provides the answer. It calculates the absolute theoretical limit for how much we can compress this data based on the probability of each symbol. To understand how we compress information using entropy, we first need to establish a baseline. Fixed-length coding. Imagine a simple source that generates only 4 symbols, A, B, C, and D. To distinguish between these 4 options digitally, we need binary identifiers. With 4 possibilities, we need exactly 2 bits per symbol. 2 to the power of 2 is 4. This is our codebook. It is uniform. Every symbol gets the same amount of space, regardless of how often it appears. Now, let's transmit a message. A, B, A, C, D, A. The encoding process is a direct lookup. For every A we see, we transmit 0, 0. For B, we transmit 0, 1. Then again, sending another 0, 0. We continue this for the entire stream. The encoder doesn't care about context or probability. It blindly substitutes symbols for their fixed-length codes. The result: a uniform block of digital data. Since we have 6 symbols, and each costs 2 bits, our total message length is exactly 12 bits. This is simple and robust, but as we'll see next, if we know that A is much more likely than D, this rigidity becomes wasteful.
To solve this, we need a smarter rulebook. We move to variable length coding. The strategy is simple but powerful. We assign the shortest possible code, just a single bit, 0, to our most frequent symbol, A. For the less frequent, B, we use 2 bits. And for the rare, C, and D, we use 3. Now, let's look at our message. A, B, A. In the old fixed-length system, every symbol took 2 bits. That cost us a total of 8 bits. But watch what happens with our new codes. A costs just 1 bit. The next, A, 1 bit. B costs us 2 bits. And the final, A, is back to 1. By tailoring the code length to the probability, our total size drops to just 5 bits. We haven't lost any information, but we have saved significant space simply by being efficient where it counts.
To ensure our data is decoded correctly and efficiently, our codes must satisfy a crucial constraint known as the prefix property. Let's look at why this matters. On the left, we have an ambiguous code. We've assigned it to 0 and B to 0-1. Suppose our computer receives a 0. Is this the letter A? It matches A perfectly. But wait, 0 is also the start of B. If the next bit is a 1, this should have been B. The decoder gets stuck, not knowing whether to finalize A or wait for more data. This ambiguity breaks real-time communication. Now, look at the prefix-free code on the right. Here, A is 0, B is 1-0, and C is 1-1. If we receive a 1, we check our list. It's not a code yet, and crucially, it's not the end of any other shorter code. So we safely wait for the next bit. We receive a 0. The sequence is now 1-0. This matches B exactly. And because no other code starts with 1-0, we can decode it instantly without looking ahead. This is the prefix property. No code word can be the start of another code word. This simple rule guarantees that every message can be decoded uniquely and instantaneously. Now that we know how to calculate entropy, let's look at its most profound implication, the source coding theorem. Imagine a number line representing the average length, L, of the codes we assign to our data symbols. Moving to the right means longer, inefficient codes. Moving to the left means shorter, more efficient codes. Shannon proved that for any data source, there is a hard, physical limit to how short these codes can get. That limit is exactly the entropy, h of x. Compression algorithms, like Huffman coding or arithmetic coding, work by squeezing out redundancy. They push our average code length down, moving from right to left, but they hit a brick wall at the entropy value. You cannot compress data to be smaller than its entropy without losing information. Mathematically, this gives us the source coding theorem. The average length L must always be greater than or equal to the entropy h of x. This is the fundamental speed limit of the information age. To see how entropy dictates structure, let's build an optimal code, a Huffman tree for 4 symbols, A, B, C, and D. We start with their probabilities. Notice D is the rarest at 0, 1, while it is the most common at 0, 5. The algorithm is greedy. It always looks for the 2 least likely outcomes to combine first. Here, that's D and C. We merge them into a new branch. The probability of this branch is simply the sum, 0, 1 plus 0, 2 equals 0, 3. Now we look at the available list again. We have B at 0, 2, and our new branch at 0, 3. These are now the 2 smallest values remaining, so we merge them. Notice what's happening physically. The rarer symbols, D and C, are being pushed deeper down the tree. Finally, we combine our accumulated branch of 0, 5 with our frequent symbol A, also 0, 5. This brings us to the root, representing 100% of the probability space. By assigning a 0 for left turns and a 1 for right turns, we get our codes. Look at the result. It is just one step away, a 1-bit code, but D takes 3 steps. The tree structure has naturally aligned code length with uncertainty. With our Huffman tree structurally complete, we can now generate the actual binary codes for our data. This is where the geometry of the tree transforms into the language of computers. The rule is simple but strict. For every left branch, we assign a binary 0, and for every right branch, we assign a binary 1. Now, to find the unique code for any character, we simply trace the path from the root at the top, down to the character's leaf. Let's start with A. We take just one step to the left, so the code for it is simply 0. Because O was our most frequent character, it stays near the top and gets the shortest possible code. Now for B. We go right, which gives us a 1, and then left, which gives us a 0. The code for B is 1-0, 2 bits. Finally, for our less frequent characters, C and D, we have to travel deeper into the tree. For C, the path is right, right, left, resulting in 1-1-0, and for D, it's right, 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 giving us 1-1-1. Notice the result. The most common data uses only 1 bit, while rare data uses 3 bits. This variable length is the secret to compression, spending fewer bits where it counts the most. Let's apply this concept of entropy to something we use every day. Language. Consider this incomplete phrase. Even with nearly 30% of the characters missing, you probably already know what it says. Because English has structure, rules of spelling and grammar, the characters are not independent. Your brain uses context to predict the missing information with high probability. In information theory, we call this redundancy. Now, let's quantify this predictability in terms of bits. If every character in a message were chosen completely at random from the 26 letters of the alphabet, the entropy would be maximum, the log base 2 of 26. That gives us about 7 bits of uncertainty per character. You'd have no way to guess what comes next. But because of the redundancy we just saw, Claude Shannon estimated the true entropy of English text to be much lower. It's actually around 3 bits per letter. This massive difference is exactly why we can compress text files so effectively. Most of the data is just confirming what we could already guess. To understand the true power of entropy, we must look at it through the lens of Claude Shannon's general model of communication. Every communication task begins with an information source, which generates a message, and a destination, the entity waiting to receive it. The goal is simply to get the message from left to right, but raw information rarely travels well on its own. It needs to be translated. We pass the message to an encoder, and eventually, a decoder will reverse the process at the other end. Between them lies the channel. This is the physical medium, a copper wire, a radio wave, or a fiber optic cable. And in the real world, channels are never perfect. They suffer from noise, random interference that corrupts what we send. Let's trace the life of a message. The source produces a message, M. The encoder compresses this message into a signal, X, stripping away redundancy. This is where entropy dictates our limits. The signal travels through the channel, where noise distorts it, resulting in a received signal, Y. Finally, the decoder looks at this noisy signal and makes its best guess, M hat, attempting to reconstruct the original. Shannon showed that this entire system is governed by 2 fundamental numbers: the entropy of the source, which tells us how much we can compress at the encoder, and the capacity of the channel, which tells us how fast we can reliably transmit despite the noise. Now that we understand how to measure information at the source, we face a new challenge. The real world is messy. When we transmit data, we send it through a channel. On the left, we have our input, X, the message we intend to send. On the right, the output, Y, the message effectively received. In an ideal world, if we send a 0, we receive a 0. If we send a 1, we receive a 1. We call this the probability of success, or 1 minus p. But physical channels, whether copper wires, fiber optics, or radio waves, introduce noise. This noise creates a chance that a 0 might accidentally flip to a 1, or vice versa. This creates a crossover. The probability of this specific error is denoted as p. Because the probability of flipping a 0 is usually the same as flipping a 1, we call this the binary symmetric channel. Most of the time, our bit travels safely across the straight path, but occasionally, entropy interferes. The bit follows the diagonal path, and the receiver gets the wrong symbol. This uncertainty, this noise is what information theory aims to overcome. Building on our understanding of mutual information, we arrive at the fundamental limit of communication. This is channel capacity. Mathematically, we define capacity, denoted as C, as the maximum possible mutual information between the input X and the output Y. But what does this maximization actually mean? To visualize this, let's stop thinking about probability distributions for a moment and think about plumbing. Imagine our channel is a pipe. We pour data into the input X. Ideally, everything we put in flows perfectly to the other side. However, real-world channels are never perfect. They have imperfections, leaks. In information theory, we call this noise. Notice that not every particle makes it across. The uncertainty introduced by the channel means some information effectively escapes or gets distorted. Now, look at the volume of flow. At the start, we have the source entropy, h of x, the total uncertainty we want to resolve. But at the end, the stream is narrower. This remaining flow is the mutual information, I of x, y. It is the useful stuff that actually survived the journey. Channel capacity, then, is simply the wideness of this output pipe. It is the theoretical upper limit on how much useful information we can push through, given the unavoidable leaks caused by the noise. To understand how we fight entropy in communication, let's look at the simplest strategy, the repetition code. Imagine we need to transmit a single bit of information, a 0, across a chaotic universe. If we send just one bit, it's fragile. So we introduce redundancy. We don't just whisper the 0, we shout it 3 times. As these bits travel through the channel, noise interferes. Thermal fluctuations or signal interference might flip a bit. What arrives at the receiver is inconsistent. 0, 1, 0. The perfect copy is lost. But because we have redundancy, we don't panic. The decoder looks at the group and takes a majority vote. 2 zeros outweigh the single error. The system assumes the 1 is noise and corrects it back to 0. We successfully recovered the message. The cost? We had to send 3 times as much data. In information theory, this is the fundamental trade-off. We sacrifice rate to gain reliability. But here is where Shannon dropped a bombshell on the world of engineering. A result so surprising it's called the noisy channel coding theorem. Let's visualize this. On our horizontal axis, we have the rate, r, essentially how fast we try to push data through a system. On the vertical axis, the probability of error, p sub e. Every communication channel, whether it's a fiber optic cable or a smoky signal fire, has a fundamental speed limit. Shannon called this the channel capacity, C, determined by the channel's bandwidth and signal-to-noise ratio. Intuition tells us that as we send data, some noise is inevitable, so error should always exist, right? Wrong. Shannon proved that as long as your transmission rate, R, stays below this capacity C, the probability of error doesn't just stay low. It can be driven arbitrarily close to 0. We can achieve essentially perfect communication, even in the presence of noise. This is a mathematical certainty. If R is less than C, error vanishes. However, if you get greedy and try to transmit at a rate higher than C, the theorem bites back. The probability of error shoots up towards 1. Communication becomes impossible. This creates what we call the achievable region. Before Shannon, engineers fought noise by just shouting louder. Shannon showed us that we don't need more power, we just need to be smart enough to stay within the speed limit of the channel. Building on our understanding of entropy as uncertainty, let's take this into the realm of modern data science and machine learning. Imagine we have a true probability distribution of data, which we'll call P. This represents reality. Now, suppose we have a machine learning model trying to predict this reality. It produces a predicted distribution, Q. Currently, our model is imperfect. It's predicting the wrong shape and location. To teach our model, we need to measure how bad this prediction is. We use a metric called cross-entropy. In information theory, cross-entropy calculates the average number of bits needed to encode data coming from the true source P, if we incorrectly use a code optimized for our prediction Q. But here is the crucial insight. We can mathematically split this cross-entropy into two distinct parts. The first part is just the entropy of P. This is the inherent uncertainty of the data itself. We cannot change this. It is the irreducible noise of reality. The second part is the Kullback-Leibler divergence, or KL divergence. Visually, you can think of this KL divergence as this gap or mismatch between our prediction and reality. It represents the extra bits, the information loss caused strictly by our model's inaccuracy. Since the entropy of P is fixed, minimizing cross-entropy is mathematically identical to minimizing this KL divergence. So, when a neural network learns, it is simply trying to squash this divergence to zero. As our prediction Q approaches the truth P, the divergence vanishes, and our cross-entropy reaches its minimum possible value, the true entropy of the data. Throughout this journey, we've seen that information isn't just abstract data, it is a physical quantity rooted in probability. We began with the simple coin flip, the fundamental unit of surprise that gave us the bit. Claude Shannon captured that slippery concept of uncertainty in a single, elegant equation. This definition revealed the path to perfect efficiency, showing us how to compress data by stripping away redundancy. And it defined the absolute speed limit of the information age, telling us how much can be sent reliably, even through the noisiest channels. In the end, entropy is more than just a measure of disorder. It is the fundamental law that measures the limits of the possible.